Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 5 on like terms. Like terms is certainly something that you've seen before in previous units on algebra. Hopefully this is the first time you've taken an algebra course, but we're going to be taking a look at like terms today, how to combine like terms, what are like terms, etc. So let's launch right into it. This is an important topic. Let's take a look, right? An algebraic term. First, before we get into what are like terms, let's make sure we know what an algebraic term is. An algebraic term, or what we'll call just a term, is a combination of numbers and variables using only multiplication, division, and exponents. Now, of course, exponents are just repeated multiplication, so quite frankly, it's, basically multiplication and division. Terms are always separated by addition and subtraction. All right, and it's important to be able to look at an algebraic expression and go, well, there's a term, and there's a term, because we often want to think of terms as a single thing, a single entity, if you will. So let's take a look in exercise 1 at just some terms. Exercise 1. For each expression below, state the number of terms it has and name it as a monomial. A monomial is something with one term, a binomial, which is something with two terms, or a trinomial, something with three terms. All right, this is fairly simple, right? But let's talk about how one would go about doing it. In letter A, let's take a look. All right, so what do we have in letter A? When we look at this expression, what we have is we have 5 times x, 3 times y, and then we've added them, right? And the key here is that what we've done, right, is we've got a term here and a term here. So this is 2 terms, which means it's a binomial, right? And this really stems from order of operations, right? The 5 times x and the 3 times y comes before the addition, all right? And so at the end of the day, we want to look at 5x and 3y as separate things, right? 5x is one thing, 3y is another thing, and we're adding them together. It's a binomial. All right. What I'd like you to do is pause the video now, think about the rest of these things, figure out how many terms there are and whether the thing is a monomial, a binomial, or a trinomial. Pause the video for a moment. All right, well, notice in letter B that there is no addition, okay, or subtraction. It's just 7x squared. So this is a term just all by itself. Right? There is simply one term, and therefore that is what we call a monomial. Right? Mono, meaning one. Right? A monomial. In letter C, we've got 4x squared, we've got x divided by 2, and we've got the number 8, and they're being separated by a subtraction and an addition. All right? So this thing has 3 terms. Right, here's a term, here's a term, and here's a term. So there are 3 terms, and it is a trinomial. Finally, in letter D, we have an x squared, which is just x times x. We have a y squared, y times y, and they're separated by the subtraction. So there are 2 terms, x squared and y squared, and this is then a binomial. Now the title of the lesson today is like terms. So let's get into what like terms are. Very important idea. Like terms are algebraic terms that contain the same variables raised to the same exponents, all right? And it's very critical to be able to look at 2 terms and immediately know if they're like terms or not. So for example, 8c and 1/2 c are like terms. They both contain the variable c, and c is being raised to the same power, to the first power. Terms can certainly contain more than one variable. For instance, 7x squared times y and negative 2x squared times y are like terms. They both contain the variables x and y, and both of those variables are raised to the same powers in both terms. X is raised to the second power, in this case y is raised to the first power, which is why we don't write it. On the other hand, something like 5x cubed and 10x squared, those are unlike terms. Even though they have the same variable, x and x, since this one is being raised to the second power and this one's being raised to the third power, they aren't like terms. Also, 9x squared and 4y squared are not like terms because even though they have variables raised to the same power, i.e. the second power, those variables are not the same variable. One of them's x, one of them's y. All right, so simple recognition. Let's take a look at the next exercise where you figure out whether or not the two terms given are like terms or not. Pause the video now, and why don't you try each one of these problems? Tell me whether they're like terms or unlike terms. All right, well, the first one, 7y squared and 2x squared, those are unlike terms, right? Even though the y and the x are both being raised to the second power, they're unlike terms because they do not have the same variable. Unlike terms. In letter B, on the other hand, we have x to the 7th divided by 3 and negative 2x to the 7th. In that case, we have the same variables, x and x, and they're being raised to the same power, to the 7th and the 7th. I know that's pretty small on your screen when we're zoomed out like that, but these are like terms. Again, it's all about looking at the variables and whether they are the same variable raised to the same power. Letter C, we've got x to the second and x to the first. Same variable, x in both cases, but one of them's to the second power, one of them's to the first power. They are unlike terms. And finally, right, in our last situation, we have 8x cubed times y squared and negative 4y squared times x cubed. Now, when you look at this at first glance, it may seem like these are unlike terms, but if you really hone in on it, right, we've got the same two variables, x and y, and they're being raised to the same powers. I've got x to the third, y to the second, y to the second. Now, you might say, well, wait a second. In this case, we've got 8x to the third, y to the second, and in this case, we've got negative 4y to the second, x to the third. You might think to yourself, well, they're not written in the same order. Here the x comes first, the y comes second. Here the y comes first, the x comes second. Well, that makes no difference because of the commutative property of multiplication, right? We've got x cubed times y squared, and we've got y squared times x cubed. We could certainly rewrite the second one equivalently as negative 4x cubed y squared. That's just, again, the commutative property of multiplication, right, that allows us to switch around that multiplication, and now we can really see that those two are like terms. Okay. So what's the point, right? So what? Some terms are like terms, some terms are unlike terms. Well, let's get into the point of why we even care about like terms. We care about them because we can often combine like terms that are being added or subtracted from one another, right? And we do this in order to make expressions simpler. And it's very easy to do because all we have to really do is add or subtract their coefficients. Let's take a look. Right? And we did this before in a previous exercise. Exercise number 3. Simplify each expression below by combining like terms. Some of your answers will be monomials, right? So it's easy. I've got 10x plus 3x. I've got 13x, right? All I'm doing is saying I've got 10x's added together. That's what 10x means. I've got 3x's added together. That's what 3x means. So if I add 10x's to 3x's, I have 13x's. All right. Likewise, if I have 9y, which is 9y's, minus 7y, I've got to have 2y's. That's just the deal. If I had 9 oranges minus 7 oranges, I would have 2 oranges. It's exactly the same thing here. 9y minus 7y is 2y. we cannot do that with unlike terms. X plus x squared is just x plus x squared. There's absolutely nothing you can do to combine those two unlike terms. On the other hand, if I have 10x plus 3x, I can say that's 13x. Simple enough. Letter C, right? I have negative 8x squared plus positive 3x squared. I can just think of this as negative 8 plus 3 is negative 5, so I will have negative 5x squared. Obviously, our life becomes more complicated when we have more than just two things being added or subtracted together. So let's take a look at D together. All right? In D, we have 6x plus 3y minus x plus 8y. I can use the commutative and associative properties to rewrite this expression as follows. Now, the x terms, those are like terms, and the y's, those are like terms, so I can combine them. Here's the associative property, right? I can group them in this way. 6x minus x is 5x, 3y plus 8y is 11y, and I get 5x plus 11y. Simple enough. What I'd like you to do now is pause the video and see if you can work out letter E and letter F on your own. Take a moment. All right, again, I'm going to use a little commutative, associative, all of that here. So move this up to the top of the board so that we can see it a little bit better, get a little bit more room. Here we go. So I'm going to rewrite this as 4x squared minus 6x squared plus 5x minus 2x. I do this because those x squareds are like terms and those x to the first are like terms. Now I can say 4 minus 6 is negative 2, x squared. 5 minus 2 is positive 3, and I just get negative 2x squared plus 3x. Likewise, in letter F, we've got a lot going on here. We've got x's to the first, y to the first, z to the first. Again, I'm going to rearrange these using the commutative properties and the associative properties. I've got 12x minus 8x minus 7y plus 2y and 3z minus z. I cross my z's so they don't look like 2's. 12x minus 8x is 4x. Negative 7y plus 2y is minus 5y. And 3z minus z is a positive 2z. I think that's it. All right, so combining like terms. Very important, basically for one simple reason, right? This expression is far more complicated than this expression, right? If I'm doing something, I'm trying to graph the equation of a line or solve an equation or something like that, I almost always want to take more complicated expressions and make them into simpler expressions. Now, why can we combine like terms? Why can't we just simply take the coefficients and add them or subtract them? And I've made some, kind of flip arguments like, well, if I've got 9 oranges plus 3 oranges, I have 12 oranges. So if I have 9x plus 3x, I have 12x. And that is not a bad way to look at it. But technically speaking, the reason we can combine like terms is something that we saw really from the past lesson, because we can run the distributive property backwards. Okay, and here's what I mean by that. Let's take a look at exercise number 3 real quick. For each binomial expression below, write it as a product of the terms GCF and another binomial. In letter C, the GCF will be a variable instead of a constant. All right, so this is just from a previous lesson where we were writing expressions in their factored form. So if I looked at 6x plus 12y, right? The GCF of 6 and 12 is going to be 6, so I could rewrite this as 6 times x plus 2y, right? Likewise, if I look at letter B and I look at 8 and 4, right? The GCF of those two terms is 4. I could rewrite this as 4 times 2n plus 1. Now here comes the one that really matters. If I look at 5x plus 3x, I can rewrite that here. The GCF isn't a number, it's a variable, right? Both of those are being multiplied by x. I can rewrite that as x times 5 plus 3. Now, clearly, unlike the first two examples, A and B, in this case, when I factor an x out of both 5x and 3x, I could actually add the 5 and 3 together, right? I could actually say, oh, well, but 5 plus 3 is 8. And that really goes to show why I can combine like terms. Because ultimately speaking, right, when I have like terms, I could take that variable with its power, or variables with their powers, and I could factor them out of each one of the terms, and then just combine their coefficients like I did here. Now you might say, well, why would I do that? You know, I can just add or subtract the coefficients, no big deal. Well, you'd want to do it for two reasons. One of which is because you want to understand why you can do that. Not just how, but why. Knowing how to do something versus why you do something, right? Those are completely different things in math, and it's way more powerful to know why than simply to know how. And the other reason we'll see a little bit later. So let's take a look at how this process might go. Exercise number 4. Combine each of the like terms by first using the distributive property to factor out the portion of each like term containing a variable. Show your work. All right, so let's do a few of these together, okay? Letter A. I have 8x minus 5x plus 7x. I could rewrite this as x times 8 minus 5 plus 7, right? I'm just running that distributive property backwards. Okay, that's 8 times 5 minus 7 is 3 plus 7, sorry, 8 minus 5 is 3 plus 7 is 10. I don't want to leave it as x10. I'm going to rewrite it as 10x. Don't get me wrong, in like all practical settings, you'd probably look at it this way. 8x minus 5x is 3x, 3x plus 7x is 10x, right? But the reason we can do that is that we can factor an x out of each one of these terms and then combine their coefficients to be left with just 10x. Let's take a look at a more complicated one in letter B. Right, in letter B, we have a few different terms going on. We've got a term involving the variable n and a term involving the variable m. So in the first case, we could factor out an n, giving me 2 minus 8. In the second case, we could factor out an m, giving me 5 plus 8. 2 minus 8 is negative 6. Remember, that's not n minus 6, that's n times negative 6. In the second case, we have m times 13. So ultimately, we have 6n plus 13m, or 13m minus 6n regardless. Okay, so what I'd like you to do is play around with the rest of the problems in this exercise. I know this takes more time than simply just adding and subtracting the coefficients, and in letter D and letter E you suddenly have some decimals and fractions involved, but I know you can do this. Pause the video now and take a shot at it. All right, letter C is pretty easy. We've just got negative 2x squared plus 11x squared, so just two terms, simple enough. All right, in this situation, what I'm going to do is I'm going to factor out an x squared and be left with negative 2 plus 11, right? X squared times 9, and that's just 9x squared. Ooh. Pen got a little stuck there. Let's take a look at letter D. Oh, fractions. Right? In this case, every one of those just involves an x, so it'll be x times 1/2 plus 3/4 minus 1/3. I now have to just combine these fractions by getting a common denominator. I would encourage you to do some of this simple fraction work by hand as opposed to on your calculator, just to get some practice with some basic arithmetic, right? 1/2 is 6/12, 3/4 is 9/12, 1/3 is 4/12. And now I can say 6/12 and 9/12 is 15/12, minus 4/12 will be 11/12. After a while, 12 sounds funny to me. I have 11/12 x. That definitely sounded weird. All right, in letter E, we've got a bunch of decimals, but they all have n as their variable, so I could factor an n out. and I'd have 8.2 minus 6.1 plus 3.4. Again, obviously you could use your calculator for this, but I would encourage you to just think about it. 8.2 minus 6.1 is 2.1. 2.1 plus 3.4 is 5.5. So we get 5.5n. Certainly use your calculator to check. And in the final problem, we have two types of like terms. We have like terms involving x squared, and then we have like terms involving just x to the first. I might rewrite these a little bit just to make sure those like terms are sitting next to each other. Again, in this situation, what I'm doing is I'm using both associative and commutative properties of addition. Once I have it written that way, I could factor an x squared out of the first two terms, giving me 7 minus 4. And I could factor an x out of the second two terms, giving me negative 5 plus 8. I'll then have x squared times 3 plus x times 3. I never leave those coefficients as the second part of a term. 3x squared plus 3x. All right, that's it. Again, I want to emphasize, in most situations, right, we will likely combine like terms by just looking at the coefficients, adding or subtracting them, and saying, hey, I've got 2x plus 3x, I've got 5x. I probably won't put in some intermediate line factoring out the x, then adding the 2 and the 3. But it's important to note, this is why we can combine like terms. This is truly the why instead of the how. And it can pay off in our final problem. Sometimes when we combine like terms, the coefficients themselves, remember a coefficient is a number multiplying a variable. That's all it is. A coefficient is a number multiplying a variable. So if I have 7x, the coefficient is 7. If I have 1/2 x, the coefficient is 1/2. Sometimes the coefficients themselves are unknown, and that can then get very confusing when we want to try to combine like terms. Let's take a look at exercise number 5. For each expression below, where x is the variable, combine the like terms and leave in terms of the unknown constants a, b, and c. Show your work. All right, so in letter A, I have a times x plus 2 times x, ax plus 2x. And that's kind of confusing, because if I had 7x plus 2x, I'd just be like, well, I have 9x, right? But ax plus 2x is a bit more confusing, unless you use the approach we did in the last problem. In which case, what you end up getting, right, is you can factor an x out, and you get x times a plus 2, and then I'm going to rewrite that as a plus 2x. It almost looks like an a, right? Almost. Or some funny looking capital Q. I don't know. Anyway, it's easy enough to combine coefficients we know, like 2, with coefficients we don't know, like a, to combine like terms if we just use this sort of factoring method. See what you can do on letter B and letter C. Pause the video now. All right, well, same song, second verse. In letter B, all right, I'm going to factor an x out of each one of these. I'll get 7 minus b minus 2. Unlike in the last problem, I can actually combine these two numerical coefficients. So 7 minus 2 is going to be 5. I still have that minus b. And so ultimately, my answer is 5 minus b times x. In letter C, all I have is unknown coefficients. But again, that almost makes it easier. I can factor an x out, and I have a plus b minus c, and that's almost my final answer. Right? I have a plus b minus c times x. This skill is strangely relevant and important in lots of algebraic problems. There are many problems where maybe you don't know the coefficient of a particular variable of interest, and you have to do this kind of manipulation in order to somehow figure out what that value is. And it goes all the way through math, all sorts of levels of math where you might have to do this kind of manipulation. All right, let's summarize. What were we looking at today? We were looking at variables and expressions. No, we weren't. Wrong title on this one to end. We were looking at like terms, all right? And in like terms, what like terms are is terms that have the same variables raised to the same powers. The same variables raised to the same powers. And it's important to be able to recognize like terms because they're the only ones that we can combine using addition and subtraction. And we often will combine like terms using addition and subtraction in order to write equivalent expressions that are simpler than what we began with. We'll see this skill a lot in future lessons, not just Unit 1, Lesson 5, or Unit 1, Lesson 1, but in many, many future lessons. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.